Assalamualaikum and hi everybody, we meet again. This is tutorial 02 and in this tutorial 02 I'm going to cover tutorial for chapter 2, part B and also part C. Part B is on ideal gas, compressibility factor and other equations of state, and part C is specific heat. Question number 1. A 1 meter cube tank contains air at temperature and pressure of 25 degrees C and 500 kilopascal respectively. This tank is connected through a valve to another tank also contains air but with known mass of 5 kg at temperature and pressure of 35 degrees C and 200 kilopascal respectively. Now the valve is opened and the entire system is allowed to reach thermal equilibrium with the surrounding, which are at temperature of 20 degrees C. We take the gas constant of air is equal to 0.287 kJ per kg Kelvin. A. Determine the volume of the second tank. B. Calculate the final equilibrium pressure of air. So from the question, we can see that there are two tanks. So I will label this tank is tank A and also tank B. And it is connected through a valve. For tank A, the temperature is 25 degrees C and the pressure is 500 kilopascal. Meanwhile, for tank B, the temperature is 35 degrees C and the pressure is 200 kilopascal. From the question, it is given to you the volume for tank A is equal to 1 meter cube and also the mass for tank B, which is 5 kg. So from the question as well, when the valve is open, the entire system, which is tank A and so tank B, will reach thermal equilibrium. So when the valve open, the tank A will reach 20 degrees C and also the tank B is also 20 degrees C, which is it is equilibrium with the surrounding. When the valve is closed, so we label as state 1, and once the valve is open, we label as state 2, and the mass for state 2 will become mass of tank A plus mass of tank B. The volume for state 2 is equal to volume for tank A plus volume for tank B. So now we go to question A. We have to find the volume of the second tank, which is tank B. So in order to find the volume for tank B, we have to consider that the air inside this tank B is ideal gas. When the temperature given is higher than the T critical and the pressure is less than the P critical, we can consider that gas is ideal gas. So when we look at tank B, the temperature is 35 degrees C and the pressure is 200 kilopascal. When we compare with T critical and supercritical, so we can consider that the air inside this tank B is ideal gas. So we can use the ideal gas equation. We have the ideal gas equation, PV is equal to mRT. So in order to find VB, so we just rearrange this equation, we become MB R B and also PB. MB is 5 kilo, TB is 35 degrees C and PB is 200 kilopascal. So when we have substitute all the info inside this ideal gas equation, so we can get the answer for volume is 2.21 meter cube. So this is the volume for second tank. Question B. We need to find the final equilibrium pressure of air, in which we need to find the pressure at state 2. So how? Because of we already consider the air is ideal gas, so we can just use the ideal gas equation, which is, so just like I mentioned to you just now, because of this is already equilibrium, so mass at state 2 is equal to mass for tank A plus mass for tank P equal to volume. So volume at state 2 is equal to V for tank A and also V for tank B. So after we have rearranged the ideal gas equation, it will become like this. So we need to substitute all the info inside, which is M2, V2 and also T2. So T2 here is 20 degrees C. So just that we need to find what is M2 and also V2. So we want to find what is M2. So we need to find first the MA, because of MB is given, we need to find the MA. So how to find the MA? Same, we can use the ideal gas equation. So we have found the MA, which is 5.85. So in order to find the M2, we just add MA, which is 5.85 kg with MB, which is 5 kg. So we will get 10.85 kg. So this is M2. So we substitute here 10.85 kg. The T is 20 degrees C, and the V here is equal to VA plus VB. So VA is 1 meter cube and VB we have already found from question A, which is 2.21. So the V2 is equal to 1 meter cube plus 2.21 meter cube. Then we get so that is how we solve question number 1. Next, question number 2. A 0.016773 meter cube tank contains of 1 kg of refrigerant 134A at 110 degrees C. Determine the pressure of the refrigerant using A. the ideal gas equation, B. the generalized compressibility chart, and C. the property table. So in this question, we need to find pressure by using 3 different methods, which is ideal gas equation, generalized compressibility chart, and also the property table. So we look first at the ideal gas equation, because we are using the ideal gas equation. So we just write down the ideal gas equation. So the temperature given is 110 degrees C. The volume is 0.016773 and the mass is 1 kg. So we rearrange the ideal gas equation, we become, so we just substitute all the info inside 1 kg. So R we use 0.08149 and temperature is divided with volume 0.016773. For information, this R is taken from table A1 and we get 1.61 kilopascal. So this is how we use the ideal gas equation. So next, we use the compressibility chart. So in this question, we are given with temperature and also volume. So in order to find the pressure from the compressibility chart, we know that the x-axis is PR, which is P reduced. So in order to find P, we know that the equation for PR is equal to P over P critical. So when we rearrange, it is equal to PR multiplied with P critical. So first, we need to find PR from the compressibility chart. So from the compressibility chart, we should have at least 2 info. It is either T, V or P, and because of we want to find P, we can use the info T and also V here. First, we need to find the T reduced, which is T over T critical. So the T critical we can get from table A1. So T given here is 110 degrees C or 388 Kelvin, and the T critical is 374.2 Kelvin for tetrafluoroethane. Then we get TR is 1.023. But for V reduced, we can find through the equation of V actual over R T critical over P critical. So the T critical and so P critical we can find from table A1. V actual is 0.016773. So the R we get just now is 0.08149 for refrigerant. This is T critical we get from table A1, and this is P critical for refrigerant, which is also we get from table A1. So we substitute all together, then we will get the answer for VR is 2.24. So now we have two info, which is VR and also TR. So we go to compressibility chart, we can find the PR from that. So from the compressibility chart, when we use TR and so VR, we will get the PR is equal to 0.39. So from this PR we can find the P. So P is equal to 0.39 multiplied with the P critical width. So P is equal to 1583 kilopascal. So this is how we use the compressibility chart to find the pressure. C, we find P from the property table. So the temperature is 110 degrees C. V is 0.016773 meter cube. So first we look at table A11. When we check at table A11, the temperature here is higher than the temperature maximum that we can get from the table A11. So means that this temperature is higher than the T saturated. So according to the first condition, T over than T saturated, so it is superheated. So when we know the phase, we go straight to table A. So from table A13, when we look at temperature 110 degrees C and we find the location of V is equal to 0.016773, so we have found that 1600 kilopascal. So that is how we find the pressure. Question number 3. Determine the temperature of steam inside the tank if it is known that the volume of the tank is 1 meter cube. The mass of the steam is 2.841 kg and the pressure is 0.6 megapascal using the following methods: A. Steam property tables, B. Ideal gas equation of state, and C. Van der Waals equation of state. From this question, it is given to you the pressure is 0.6 megapascal, volume is 1 meter cube, and the mass is 2.841 kilogram. So first we need to find the temperature from the property table. Because we want to find from the property table, we have to use the pressure, which is 0.6 megapascal, and we need another info, and from here you are given with V and also M, so we can find the specific volume. So the specific volume we can find from V over M. So then we will get 0.3520 meter cube per kg. So from here we have already two info, which is P and also V. So we go to table A5, we check at pressure 0.6 megapascal or 600 kilopascal. So after we have checked, the V here is over than Vg. So according to the first condition, it is superheated. So because of it is superheated, we have to go to the table A6. We look at pressure 0.6 megapascal and we find the location of V of 0.3520 at which temperature. So after we have found that, the temperature is 200 degrees C or 473 Kelvin. So that is how we find from the property table. B, we need to find the temperature by using ideal gas equation. PV is equal to RT. This V is specific volume, and the specific volume we have found just now, which is 0.3520 meter cube per kg. So we just substitute in to find the temperature. We rearrange the ideal gas equation, PV over R. So R we get from table A1, the gas constant for water. So we substitute, then we solve it, it will become 457.6 Kelvin. So this is how we find from the ideal gas equation. Next, we find using the van der Waals equation. So first we have to know what is the equation for van der Waals. So this is equation for van der Waals. If you look at here, we have R, in which we just get from table A1. The P is given, V is specific volume, A and B we can get from this equation. This is the equation for A and also B. So in this equation, you can see here there are T critical, P critical. So the T critical and P critical we can find from table A1 for water. So the calculation for van der Waals is very straightforward. In order to find T, we need to find first the A and also B. So after we get the A and also B, we substitute in here. Then we solve T, and T we will get is equal to 465.9 Kelvin. So that is how we solve question number 3. So now we go to part C, specific question number 1. Determine the enthalpy change delta H of nitrogen in kilojoule per kg as it is heated from 600 Kelvin to 1000 Kelvin using these three methods. A. The empirical specific heat equation as a function of temperature, which is table A to C. B. The CP value at the average temperature, table A to B. And C. The CP value at room temperature 300 Kelvin, table A to A. So from the question, we are going to find the delta H, in which the delta H we know that it is equal to the integration of CP dt. Given in the question, it is heated from T1 is equal to 600 Kelvin and T2 is 1000 Kelvin. So for A, we need to find the change of enthalpy by using this equation. We have to look at table A to C, in which in table A to C we have found that in order to find the CP, it is equal to A plus B T plus C T to the power of 2 plus D T to the power of 3. So we need to use this equation. So from table A to C, refer at nitrogen and we find all the A, B, C and D constant. So to find the delta H, we need to integrate this CP, in which it will become like this. So we need to integrate this equation. So we need to integrate this CP from T1 to T2. So it will become like this. So from table A to C, we find one by one the A, B, C and also D, and this T2 is 1000 and T1 is 600 Kelvin. After we have substituted all the value inside this equation, we solve it, then we will get the delta H is equal to 12544 kilojoule per kilomole. So according to the question, we need to find the enthalpy change in kilojoule per kg. So this delta H, we need to divide with its molecular weight. And the molecular weight for nitrogen is 28.013 kg per kilomole. Then after we solve, we will get 447.8 kilojoule per kg. Next, B, we have to find by using table A to B. But by using this table, we don't have to integrate. So we just use this equation. Just that we have to find the CP average. But how to find the CP average? We can find from by using CP, we find at the T average. So the T average is just 1000 plus 600 divided by 2, which is 800 Kelvin. So the T average is 800 Kelvin. So means that we have to find the CP at 800 Kelvin. So from table A to B, the CP at 800 Kelvin is equal to 1.121 kilojoule per kg Kelvin. So we just substitute in this equation, so we can find the delta H is equal to 448.4 kilojoule per kg. So that's how we use table A to B. For C, we need to use the value for Cp from table A to A. So because of this table A to A is available for 300 Kelvin, so we just take the Cp at 300 Kelvin for nitrogen. So the Cp is equal to 1039 kilojoule per kg Kelvin. So we just straight away calculate the delta H is equal to Cp T2 minus T1. Then we will get 415.6 kilojoule per kg. So that's how we use the table A to A. Question number 2. Determine the internal energy change delta U of hydrogen in kilojoule per kg as it is heated from 200 Kelvin to 800 Kelvin using these three methods. A. The empirical specific heat equation as a function of temperature, table A to C. B. The CV value at the average temperature, table A to B. And C. The CV value at room temperature 300 Kelvin, table A to A. In this question, we need to find the delta U. We know that delta U is equal to CV dt. For question A, we need to use a table A to C, in which we have to do the integration of CV. But in table A to C, we can see that the only equation that we have is Cp, but we need to use the CV. So how should we do? We have to remember the relation of Cp and Cv by using this equation, which is Cv is equal to Cp plus Ru. So in order to relate the Cp and so Cv, we will use Ru. So we just proceed with this equation is equal to, in which Cp is equal to this equation. So we just substitute Cp into this. So we rearrange until we get this. Next, we solve this integration. It will become like this. Next, we find all the A, B, C and D constant from the table A to C. We substitute also the temperature. So we substitute all the value inside here. Then we solve. Then we will get 12487 kilojoule per kilomole. So this is delta U. But in this delta U, we will get kilojoule per kilomole. But the question need you to calculate in kilojoule per kg. So how? We need to divide with the molecular weight. So delta U is equal to 12487 kilojoule per kilomole over the molecular weight of hydrogen, which is 2.016 kilogram per kilomole. Then you will get a 6194 kilojoule per kg. So that's how you find from table A to C. For question B, we need to find by using table A to B. So by using table A2, we need to find the CV average. So the CV average we should find from CV at T average. So the T average is 200 plus 800 divided by 2, it is equal to 500 Kelvin. So you need to find the CV at 500 Kelvin from table A to B. So we found that the CV at 500 Kelvin it is equal to 10.389 kilojoule per kg Kelvin. So we just directly calculate the delta U is equal to CV average T2 plus T1. We will get 6233 kilojoule per kg. So that is how we use table A to B. Next, question C, we need to use table A to A. So as I explained to you before, this table A to A is at temperature 300 Kelvin. Because of, we need to find from table A to A, so we just take the value for CV from that table, which is 10.183 kilojoule per kg Kelvin. So we just directly calculate delta U is equal to CV T2 minus T1. So we substitute all the value inside, then we will get 6110 kilojoule per kg. So that's how you calculate by using table A to A. So we have finished tutorial for chapter 2, part A, part B, and also part C. I hope you can understand and useful during your study. And till we meet again in the next tutorial video. Thank you.